We're going to start today in a serious way on the inhomogeneous equation. Second order linear differential. I'll simply write it out instead of writing out all the words which go with it. So such an equation looks like, the second order equation is going to look like y double prime plus p of x t x plus q of x times y. Now up to now the right hand side has been 0. So now we're going to make it not 0. So this is going to be f of x. In the most frequent applications, x is time. X is usually time. Often. But not always. So maybe just for today, I'll use x in talking about the general theory. And then from now on, I'll probably make x equal time because that's what it is most of the time in the applications. So this is the part we've been studying up till now. This is called the, it has a lot of names. It's input, signal, commas between those, a driving term. Sometimes it's called the forcing term. You'll see all of these in the literature. And it pretty much depends upon what course you're sitting in, what the professor habitually calls it. I'll try to use all these terms now and then, but probably most often I'll lapse into input as the most generic term, suggesting nothing in particular, and therefore equally acceptable or unacceptable to everybody. The response, the solution then, the solution, as you know, is going is then called the response. The response, sometimes it's called the output. I think I'll stick pretty much with response. So I'm using the same terminology we use for studying first order equations. Now, as you'll see, the reason we had to study the homogeneous case first was because you cannot solve this without knowing the homogeneous solutions. So that's the inhomogeneous case. But the homogeneous one, the corresponding homogeneous thing, y double prime plus p of x y prime plus q of x times y equals 0, is an essential part of the solution to this equation, and that's called, therefore, it has names. Now, unfortunately, it doesn't have a single name. I don't know what to call it, but I think I'll probably call it the associated homogeneous equation, or ODE. The associated homogeneous equation, the one associated to the guy on the left. It's also called the reduced equation by some people. There's some other term for it which escapes me totally, but what the heck. Now, its solution has a name, so its solution, of course, doesn't depend on anything in particular, the general solution, because the right-hand side is always 0. So its solution we know can be written as y equals, in the form c1 y1 plus c2 y2, where y1 and y2 are any two independent solutions of that, and then the c1s and c2s are arbitrary constants. Now, when you're looking at this equation, you're going to need this also, and therefore it has a name. It has various names. Sometimes there's a subscript c there. Sometimes there's a subscript h. Sometimes there's no subscript at all, which is the most confusing of all. But anyway, what's the name given to it? Well, there is no name. Many books call it the solution to the associated homogeneous equation. That's maximally long. Your book calls it the complementary solution. Many people call it that, and many will look at you with a blank who know differential equations very well and will not have the faintest idea what you're talking about. If you call it YH, then you're thinking of it as the solution. The H is for homogeneous to indicate it's the solution. So it's the solution to the, I'm not going to write that out. You put it in your books if you like writing. Write solution to the associated homogeneous equation, YH. But it's all the same thing. Now, well, the solution to the reduced equation I see I have in my notes. Okay, good. The solution to the reduced equation, too. All right, now the examples. There are, of course, two classical examples of which you know one, but use them as the model for what solutions of these things should look like and how they should behave. So the model you know already is the one, I won't make the leading coefficient 1 because it usually isn't, is the one mx double prime, so t is the independent variable, plus bx prime plus kx equals f of t. That's the spring mass system, the spring mass dashpot system. Mass, the damping constant, and the spring constant. Except up to now it's always been 0 here. What does this f of t represent? Well, if you think of the way in which I derived the equation, the mx, that was the Newton's law. That's the acceleration. So it's the acceleration, the mass times the acceleration. By Newton's law, this is equal to the imposed force on the little mass truck. Okay, you got that truck there. I'm not going to draw the truck for the nth time. You'll have to imagine it. So here's our truck. Okay, forces are acting on it. And remember, the forces were minus kx. That came from the spring. There was a force minus bx prime. That came from the dashpot, the damping force. So this other guy is f of t. What's this? This is the external force which is acting on it. In other words, instead of the little truck going back and forth and doing its own thing all by itself, here is somebody with an electromagnet, and the mass it's carrying is a big pile of iron ore, and the electron turning it on and off and pulling that thing from afar where nobody can see it. So this is the external force. Now, think that is the model you must have in your mind of how these equations are treated. In other words, when f of t is 0, the system is passive. There is no external force on it when this is 0. The system is sitting and just doing what it wants to do all by itself. You wind it up by giving it an initial push and putting its initial position somewhere, but after that you lay your hands off. The system then just passively responds to its initial conditions and does what it wants. The other model is that you don't let it respond the way it wants to. You force it from the outside by pushing it with an external force. Now, those are clearly two entirely different problems, what it does by itself or what it does when it's acted on from outside. And when I explain to you how the thing is solved, you have to keep in mind those two models. So this is the forced system. I'll just use the word forced system. That's where f of t is not 0, versus the passive system where there is no external applied force. The passive system, the forced system. Now, you have to both, even if you want to just solve the forced system, the way the system would behave if nothing were being done to it from the outside is nonetheless going to be an important part of the solution. And I won't be able to give you that solution without knowing this also. Now, I'd like to give you the other model very rapidly because it's in your book, it's in the problems I have to give you, and it's part of everybody's culture, whether they like it or not. So that's example number 1. The example number 2, which follows the differential equations just as perfectly as the spring mass dashpot system, is the simple electric circuit. with an inductance. You don't know yet what an inductance is officially, but you will. A resistance. Sorry, that's a capacitance. Okay, put the capacitance up there. The resistance, and then maybe a thing. Okay, so this is a resistance. I think you know these symbols. You know this by now. You certainly know the system for the capacitance. C is what I mean by when I say C is the capacitance. You may not know yet what L is. That's called the inductance. So this is something called a coil, because it looks like one. It has an L is what's called its inductance. And the differential equation, there are two differential equations which can be used in this, but they're essentially the same. One is simply the derivative of the other. Both differential equations come from Kirchhoff's voltage law, that the sum of the voltage drops as you move around the circuit has to be 0. Because otherwise, well, I don't have to. That's because of somebody's law, Kirchhoff, with 2 H's. The sum of the voltage drops is 0, and now you know the voltage drop across this, and you know the voltage drop across that because you learned it in 802. You will one day learn the voltage drop across this, but I already know it. So it's Li. So I is the current. I'll write this thing in its primitive form first. So I is the current. Current is flowing in the circuit. Q is the charge on the capacitance. So the voltage drop across the coil is L times I. The voltage drop across the Li prime. The voltage drop across the resistance is, well, that's, you know that. And the voltage drop across the capacitance is Q divided by C. And so that's equal to, well, it's equal to 0, except if there's a battery here or something generating a voltage drop. So let's call that E as a generic word. E could be a battery. It could be a source of alternating current, something like that. But there's a voltage drop across it, and I'm giving E the name of the voltage drop. So plus, and then there's the question of the signs, which I never understand, but let's assume you've chosen the sign convention so that this comes out nicely on the right-hand side. So this might be varying sinusoidally, in which case you'd have a source of alternating current, or it might be constant, in which that would be a battery, a little dry cell giving you direct current with a constant voltage, stuff like that. So you can make this minus if you want, but everything will be raw, have the wrong sign, so don't do it. Now, this doesn't look like what it's supposed to look like because it's got Q and I. So the final thing you have to know is that Q prime is equal to I. The rate at which that charge leaves the condenser and hurries around the circuit to find its little soulmate on the other side is the current that's flowing in the circuit. That's why current flows, except nothing really happens. Electrons just push on each other and they stay where they are. I don't understand this at all. So if I differentiate this, you can do two things. Either you can integrate I and express the thing entirely in terms of Q, or you can differentiate it and express everything in terms of I. Your book does nicely both, does not take sides. So let's differentiate it, and then it will look like Li double prime plus Ri prime plus I divided by C equals, and now watch out, you have now not the electromotive force, but its derivative. So if you were so unfortunate as to put a little dry cell there, now you got nothing, and you got the homogeneous case. That's okay. Where are the erasers? Oh. One eraser? I don't believe this. So there's the equation. There are two equations. One, we put them up in colored chalk. There's the spring equation. And here's the equation that governs the current, how the current flows in that circuit. And now you can see Again, what does it mean? If this is 0, for example, if I have a dry cell there, or if I have nothing at all in that, nothing at all in the circuit, then this represents the passive circuit. It's just sitting there. It wouldn't do anything at all, except that you've put a charge on the capacitor and waited. And of course, when you put a charge on there, it's got a discharge, and discharges through the circuit and swings back and forth a little bit if it's underdamped, until finally, toward the end, the current dies away to 0. But what usually happens is that you drive this passive circuit by putting an effective E in it, and then you want to know how the current behaves. So those are the two problems: the passive circuit without an applied electromotive force, or plugging it into the wall and wanting it to do things. That's the normal state of affairs. People don't want passive circuits. They want circuits which do things because, okay, that's why they want to solve inhomogeneous equations instead of homogeneous equations. But as I said, you have to do the homogeneous case first. Okay, you are now officially responsible for this, and I don't care that you haven't had it in physics yet. You will before the next exam, so I don't even feel guilty. But you're going to start using it on the problem set right away, so never too soon to start learning it. Okay, now, the main theorem, I now want to go, so that was just examples to give you some physical feeling for the sorts of differential equations we'll be talking about. I now want to tell you briefly about the key theorem about solving the homogeneous equation. So the theorem, the main theorem about solving the homogeneous equation is the inhomogeneous equation. So I'm going to write the inhomogeneous equation as, you make the left-hand side a linear operator, and I'm going to write the equation as Ly equals f of x. That's the inhomogeneous equation. So L is the linear operator, second order because I'm only talking about second order equations. L is a linear operator, and then this is the differential equation. So here's our differential equation. It's inhomogeneous because it's got the f of x on the right-hand side. And what the theorem says is that the solution has the following form. The solution has the form y sub p, I'll explain what that is in just a moment, plus y sub c. So the hypothesis is we've got the linear equation, and the conclusion is that that's what its solution looks like. Now, you already know what y sub c looks like. In other words, if I write this out in more detail, it would be, i.e., department of fuller explanation. The solution, general solution, looks like y equals y sub p, and then this thing is going to look like an arbitrary constant times y1 plus an arbitrary constant times y2, where these are solutions of the homogeneous equation. So yc looks like this part, and the yp is, what's yp? P stands for particular, the most confusing word in this subject. But you've got at least 4 weeks to learn what it means. Okay, yp is a particular solution. To Ly equals f of x. Now, I'm not going to explain what particular means. First, I'll chat as if you knew what it meant, and then we'll see if you have picked it up. In other words, the procedure for solving this equation is composed of 2 steps. First, to find this part. In other words, to find the complementary solution. In other words, to do what we've been doing for the last week, solve not the equation you were given, but the reduced equation. So the first step is to find this. The second step is to find yp. Now, what's yp? y per t is a particular solution to the whole equation. Yeah, but which one? Any one. Well, if it's any one, then it's not a particular solution. Yeah. I say, unfortunately, the word particular here is not being used in exactly the same sense in which most people use it in ordinary English. It's a perfectly valid way to use it. It's just confusing, and no one has ever come up with a better word. So particular means any one solution. Any one will do. Okay? Even these have slightly different meanings. Any questions about this? I refuse to answer them. Now, well, examples, of course, will make it all clear. But I'd like first to prove the theorem to show you how simple it is. It's extremely simple if you just use the fact that L is a linear operator. We've got two things to prove. What do we got to prove? Well, I have to prove two statements. First of all, that all the yp plus c1y1 plus c2y2 are solutions. How are we going to prove that? Well, how do you know if something's a solution? Well, you plug it into the equation and you see if it satisfies the equation. Goody, let's do it. Proof. L, I'm going to plug it into the equation. That means I calculate L of yp plus c1y1 plus c2y2. Now, what's the answer? That's because this is a linear operator. And notice the argument doesn't use the fact that the equation is second order. It immediately generalizes to a linear equation of any order, whatever. 47. Okay, this is L of yp plus L of c1y1 plus c2y2. But what's that? What's L of the complementary solution? What does it mean to be the complementary solution? It means when you apply the operator L to it, you get 0, because this satisfies the homogeneous equation. So this is 0. What's L of yp? Well, it was a particular solution to the equation. Therefore, when I plugged it into the equation, I must have gotten out on the right-hand side f of x. So this is since yp is a solution to the whole equation. So what's the conclusion? That if I take any one of these guys, no matter what C1 and C2 are, apply the linear operator L to it, the answer comes out to be f of x. Therefore, this proves it. This shows that these are all solutions because that's what it means. Therefore, they satisfy L of y equals f of x. They satisfy the whole inhomogeneous differential equation, and that's it. Well, that's only half the story. The other half of the story is to show that there are no other solutions. Okay, so we got our little u of x coming up again, and he thinks he's a solution. Okay, so to prove there are no other solutions. This almost sounds biblical. Thou shalt have no other solutions before me. Okay. There are no other solutions except these guys for different values of C1 and C2. Okay, so u of x is a solution. I have to show that u of x is one of these guys. How am I going to do that? Easy. If it's a solution, then L of u, I'm going to drop the x, okay, just to make like I dropped the x over there. If it's a solution to the whole inhomogeneous equation, then this must come out to be f of x. Now, what's L of y of p? That's f of x too. My secret little particular solution I've been, got in my pocket. Okay, I pull it out. Aha! L of y of p, that's f of x too. And now I'm going to not add them, I'm going to subtract them. What is L of u minus yp? Well, it's 0. It's 0 because this is a linear operator. This would be L of u minus L of yp. I get the answer 0 on the right-hand side. And therefore, what is the conclusion? If that's 0, it must be a solution to the homogeneous equation. Therefore, u minus yp is equal to, there must be C1 and C2. Oh, I won't give them the generic names. Let's give them a name, a particular one. I'll put a tilde on to indicate it's a particular one. C1 plus C2, Y2, tilde. So, in other words, for some choice of these constants, and I'll call those particular choices C1 tilde and C2 tilde, it must be that these are equal. Well, what does that say? It says that U is equal to YP plus C1 tilde, blah, 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 plus C2 tilde, blah, 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 blah. And therefore, it shows that U wasn't a new solution. It was one of these. So U isn't new, is one of. So U, I should write it down, otherwise some of you will have missed the punchline. Okay, therefore, U is equal to yp plus C1 tilde y1 plus C2 tilde y2. And it shows it's this guy who thought he was new was not new at all. It was just one of the other solutions. Okay, well now, since if the coefficients are constant, apparently we've done half the work. We know what the complementary solution is because you know how to do those in terms of exponentials and complex exponentials, sines and cosines and so on. So what's left to do? All we have to do is to solve equations which are inhomogeneous, all we have to do is find a particular solution. Find one solution. It doesn't matter which one. Any one. Just find one. Okay? Now, we're going to spend the next 2 weeks trying to do this. I'll give you various methods. I'll give you a general method involving Fourier series because it's a good excuse for learning what Fourier series are. But the answer is that in general, for a few standard functions, it's known how to do this. You'll learn those methods for finding those using operators. For all the others, it's done by a series or a method involving approximation, or the worst comes to worst, you throw it on a computer and just take the graph and the numerical output of answers as the particular solution. Okay, now before we're going to start that work, not today, we'll start it next Monday and it'll last, as I say, the next 2 weeks, and we'll be up to spring break. But before we do that, I'd like to relate this to what we did for first order equations because there's something to be learned from that. Think back to the linear first order equation. And I'm going to, since from now on for the rest of the period, I'm going to be considering the case of constant coefficients. In other words, the case of springs or circuits or simple systems which behave like those and have constant coefficients. So for the linear first order equation, there too I'm going to think of constant coefficients. We talked quite a bit about this equation. What did I call the right-hand side? I think we usually called it Q of t, right? This is an ancient history, definition of ancient history. It was before the first exam. Okay, now, how does that fit into this theorem that I've given you? Remember what the solution looked like? The solution looked like, remember you took it, the integrating factor was e to the kt, and then after you integrated both sides, multiplied through, and the final answer looked like this. Y equaled, it was e to the negative kt times either an indefinite integral or a definite integral, depending on your preference. Q of t, so x is metamorphosed into t. I gather you got that. E to the kt plus, what was the other term? A constant times e to the negative kt. How does this fit into the paradigm I've given you over there for solving the second order equation? Which term is which? Well, this has the arbitrary constant in it, so this must be the complementary solution. Is it? Is this the solution to the associated homogeneous equation? What's the associated homogeneous equation? Put 0 here. Okay, if you put 0 there, what's the solution? Now, this you ought to know by now. Y prime equals negative ky. What's the solution? E to the negative kt. Now, you're supposed to come into this course knowing that. Except there's an arbitrary constant in front. So, right, this is exactly the solution to the associated homogeneous equation where there's 0 here. Then what's this thing? This is a particular solution. This is my yp. But that's not a particular solution because this indefinite integral, has an arbitrary constant in it. In fact, it's just that arbitrary constant. So it's totally confusing. But this symbol, you know when you actually solve the equation this way, all you did was you found one function here. You didn't throw in the arbitrary constant right away. All you needed to do was find one function. And even if you really are bothered by the fact that this is so indefinite and therefore how can it be, but make it a particular solution by making this 0, make it a definite integral. 0 here, t there, and then change those t's to dummy t's, t1s or t tildes or something like that. So this fits into that thing. It's, in other words, I could have done it at that time, but I didn't see the point because this can be solved directly, whereas, of course, the general second-order equation in homogeneous cannot be solved directly, and therefore you have to be willing to talk about what its solutions look like in advance. Now, remember I said I said there was 2 different cases, although both of them had the identical looking solution, their meaning in the physical world was so different that they really shouldn't be considered as solving the same equation. And one of these was the case, of the 2, perhaps the more important was the case when k was positive, and of course the other is when k is negative. When k is positive, that had the effect of separating that solution into this part, which was a transient, and the other part, which was a steady state. The steady state solution, that was the yp part of it in that terminology. And the transient part, it was transient because it went to 0. If k is positive, the exponential dies regardless of what c is. So the transient, that's the yc part, it goes to 0 as t goes to infinity. The transient depends on uses the initial condition, whatever it is, because that's what determines the value of c. On the other hand, this initial condition makes no difference as you go, t goes toward infinity. All that's left is this steady state solution, and all solutions tend to the steady state solution. So if k is positive, one gets this analysis of the solutions into the sum of one basic solution and the others which just die away, have no influence on this, have no influence, less and less influence as time goes to infinity. For k less than 0, this analysis does not work because this term, if k is less than 0, this term goes to infinity or negative infinity, and typically tends to dominate that. So it's this term that's the important one. It depends on the initial conditions, and the analysis is meaningless. So the above is meaningless. And now what I'd like to do is try to see what the analog of that is for second-order equations and higher-order equations. But second order will be, if you understand second order, that's good enough. Higher order goes exactly the same way. So the question is, when, for second order, let's make it with constant coefficients plus our let me, B, I could call it B and K, like I did up, oh no, BK or P, and the trouble is that wouldn't take care of the electrical circuits. So I just want to use neutral letters, which suggest nothing, and you can make them turn it into circuits or springs or yet other examples undreamt of. But these are constants. And I'm going to think of it as time. I think I'll switch back to time. Let x be the time. So by equals f of t. So there's our equation. A and B are constants. And the question I'm asking, you can think of either of these two models or others. The question I'm asking is, under what circumstances can I make that same type of analysis into steady state and transient? Well, what does the solution look like? The solution looks like y equals a particular solution plus C1 y1 plus C2 y2. Therefore, to make that look like this, the C1 and C2 contain the initial conditions. This part does not. Therefore, if I want to say that the solutions look like a steady state solution plus something which dies away, which becomes less and less important as time goes on, what I'm really asking is, under what circumstances is this part guaranteed to go to zero? So the question is, when, in other words, under what conditions on the equation, A and B, in effect, is what we're asking, when does C1 y1 plus C2 y2 go to zero as t goes to infinity, regardless of what C1 and 2 are, for all C1, C2. Now here there was no difficulty. We had the thing very explicitly, and you can see it. K is positive, this goes to zero, and if K is negative, it doesn't go to zero. It goes to infinity. Here I want to make the same kind of analysis, except it's just going to take it's a little more trouble, but the answer, when it finally comes out, is very beautiful. So when are all these guys going to go to zero? First of all, you might as well have the definition. So all the good things that this is going to imply. If this is so, in other words, if they all go to zero, everything in the complementary solution goes to zero, then the ODE is called stable. Some people call it asymptotically stable. I don't know what to call it. Yeah, I can make the analysis, and then I use the identical terminology, C1 y1 plus C2 y2. This is called the transient because it goes to zero. This is called the particular solution now that we labor so hard to get for the next 2 weeks is the important part. It's the steady state part. It's what lasts out to infinity after the other stuff has disappeared. So this is the steady state solution. Steady state solution, okay? And the differential equation is called stable. Now, it's of the highest interest to know when a differential equation is stable. A linear differential equation is stable in this sense. Because you have a control, you know what its solutions look like. You have some feeling for how it's behaving in the long term. If this is not so, each equation is a law unto itself and you don't know. So, let's do the work. For the rest of the period, what I'd like to do is to find out what the conditions are which make this true. Those were the equations which we'll have a right to call stable. So, when does this happen? And where is it going to happen? I don't know. I guess here. Now, I think the first step is fairly easy, and it'll give you a good review of what we've been doing up till now. So I'm simply going to make a case-by-case analysis. Don't worry, it won't take very long. What are the cases we've been studying? Well, what do the characteristic roots look like? The roots of the characteristic equation, in other words. Remember, there are cases. The first case is they're real and distinct. R1 not equal to R2. Real and distinct. What are the other cases? Well, R1 equals R2. And then there's the case where they're complex. So I'll write it R equals A plus or minus BI. What do the solutions look like? So my ham-handed approach to this problem is going to be, in each case, I'll look at the solutions and first get the condition on the roots. So in other words, I'm not going to worry right away about the A and the B. I'm going instead to worry about expressing this condition of stability in terms of the characteristic roots. In fact, that's the only way in which many people know the conditions, though you're going to be smarter. Okay, what do the solutions look like? Well, they all look, the general solution looks like e to the R1t plus C2e to the R2t. Okay, so what's the stability condition? In other words, if the equation happened to have its characteristic roots real and distinct, under what circumstances would it be stable? Would it, in other words, all its solutions go to zero? So I'm talking about the homogeneous equation. The reduced equation, the associated homogeneous equation. Why? Because that's all that's involved in this. In other words, I'm no longer, when I write that, I'm no longer interested in the whole equation. All I'm interested in is the reduced equation, the equation when you turn the f of t on the right-hand side into zero. So what's the stability condition? Well, let's write it out. Under what circumstances will all these guys go to zero? If R1 and R2 should be negative, can they be zero? No, because then it'll be a constant and it won't go to zero. How about this one? Well, in this one, it's C1 plus C2 times t multiplied by e to the R1t. Of course, both of these are the same. I'll just arbitrarily pick one of them. What happens to this as things go to zero? Well, this part's rising, at least if C2 is positive. This part is either helping or it's hindering. But I hope you know what these functions look like and you know which of them go to zero. They go to zero if R1 is negative. They might rise in the beginning, but after a while they lose their energy and go off. Of course, if R1 is equal to zero, what do these guys do? Linear, go to infinity. Well, we're doing okay. How about here? Well, here it's a little more complicated. The solutions look like e to the at times C1 cosine bt plus C2 sine bt. Now, this part is a pure oscillation. You know that. It might have a big amplitude, but whatever it does the same thing all the time. So whether this goes to zero depends entirely upon what that exponential is doing, and that exponential goes to zero if a is negative. So here the condition is a is negative. And now the only thing left to do is to say it nicely. I've got three cases, and I want to say them all in one breath. So the stability condition is, so the ODE is stable. So this is, or f of t, it doesn't matter. But psychologically, you can put this zero there. Is stable if what? If in case 1 this is true, if case 2 that's true, in case 3 that's true, but that's ugly. Make it beautiful. The beautiful way of saying it is if all the characteristic roots have negative real part. If the characteristic roots, the r's or the a plus or minus bi, have negative real part. That's the form in which, you know, the electrical engineers will nod their head, tell you, yeah, that's right. Have negative real parts, sorry. Isn't it right? Is that right here? Yeah. What's the real part of these guys? They themselves, because they're real. What's the real part of this? Yeah. The only case in which I really have to use real part is when I talk about the complex case, because A is the real, just the real part of the complex number. It's not the whole thing.